Let's go ahead and take a look at our last part of the unit, entropy, spontaneity, the second and third laws of thermodynamics, and Gibbs free energy. So what do we mean by a spontaneous process? Well, it's one that proceeds on its own without any outside assistance. Put a piece of metal outside, especially in the rainwater, what's going to happen over time? It's going to rust. A spontaneous process only occurs in one direction. The reverse reaction is not spontaneous. I'll give you an example. If you drop an egg, it's going to break. This is spontaneous. Well, what's the reverse? The egg magically going back together in your hand? Not spontaneous. Spontaneity is affected by temperature and pressure. It does not have anything to do with the rate of reaction. It simply tells you whether or not it will go on its own. It might take a long time. It might go quickly. Just because a reaction is exothermic does not make it spontaneous. I'll give you an example. Ice melting. Ice melting is endothermic. It requires energy to go in order to turn ice into liquid water. But it's spontaneous. Spontaneous reactions are irreversible. Let's take a look at the second law of thermodynamics. It says any irreversible process results in an increase in entropy of the universe, whereas any reversible process results in no change. The entropy of the universe increases in any spontaneous process. A really simple way of thinking about this is that processes want to occur in a way that cause more disorder. Delta S, entropy, is a state function. It only depends on the initial and final states, not on the pathway taken to get there. You can find the change in entropy by looking at the final and subtracting the initial, or you can look at entropy as equal to the reverse Q, the heat for the reverse reaction. A reversible process is where the entropy of the system and the entropy of the surroundings always equals zero. They balance out. In an irreversible process, the entropy of the universe is equal to the entropy of the system, the entropy of the surroundings, but they're always greater than zero. In other words, entropy is always increasing. Let's discuss entropy. I'd like to think of entropy as disorder or chaos. Often I talk to students about, imagine you have a task. Do you want to babysit 2 children at the park or 20 children at the park? Hyped up on sugar. Right? 2 children, much easier to control. With 20 kids, one might be up a tree, another one might be out in the street. Who knows where they are? But with chemistry, we're talking about the freedom of movement of molecules. We call these things microstates, the single possible arrangement of a position and kinetic energy of a molecule. And then we look at, well, how many are there? So if you look at the first diagram, there are 2 molecules, a green and a red. There are only 4 ways you can arrange those particles in that particular setup. In the second picture, there are 4 different dots. Kind of hard to see because one is yellow. But look at all the very many ways we can arrange 4 molecules. Clearly, the more molecules, the more entropy. Let's keep going with entropy and talk a little bit more about motion. What are the things that cause more disorder? Temperature, because as temperature increases, particles have more kinetic energy, so they're moving faster, they're moving farther apart, especially if we're talking about gas molecules. If you have a bigger volume, there's more entropy. Again, I go back to little kids. If you have little kids ready to take a nap, pretty easy to control. Little kids hyped up on sugar and caffeine, pretty hard to control, a lot of chaos and craziness. It's easier to babysit 20 kids in a small room versus a large area like a park. Gases have more entropy than liquids, and liquids have more entropy than solids. But think about the particles. Solids, their molecules are barely moving. Liquids have a little bit more freedom, and gases are crazy. They're all over the place, like kids hyped up on sugar at the park. Any factor that increases freedom of movement increases entropy. So if you take salt and pour it into water, it now has more entropy because before it was in the salt shaker. Now it's in this big, huge pitcher full of water. We use delta S for entropy. And there's 3 different kinds of molecular motion we need to discuss: translational, vibrational, and rotational. Translational is where the entire molecules move in one direction. Think about like a baseball being thrown. Vibrational is just where the molecules shake. And if you look at this picture, it's just a simple water molecule. There's different ways the molecule can shake. The hydrogens can be pulling symmetrically down. They can be pulling asymmetrically. And then the hydrogen molecules can even move in and out like this. Different ways of vibrating. Rotational is just where the molecule spins. So stand up, take a spin, that's vibrational. Let's consider ice becoming water vapor, and where we see motion. In ice, the hydrogen bonding leads to a very rigid structure. Each molecule does vibrate, but translational and vibrational motions are restricted. In water, there's still hydrogen bonds, but the molecules have a little bit more freedom to move about each other, translational, and they tumble around, rotational. Well, with water vapor, the water molecules are up here in the atmosphere. They're independent of each other, and they have the full range of all 3 kinds of motion. Well, which one of those has the most number of microstates and therefore the most entropy? Water vapor. The 3rd law of thermodynamics states the entropy of a pure, perfect crystalline substance at absolute zero is 0. And that kind of goes along with the idea of ice. So let's just take a quick look and a little review again at what we've learned so far about entropy. Entropy of gases is always greater than liquids, which are greater than solids, because gases have more freedom of movement than liquids. Liquid molecules have more freedom of movement than solids. As you increase the molar mass, entropy increases. Entropy also increases with an increasing number of atoms in the formula of a substance. And that equation should look kind of familiar. It's just like delta H. And yes, there are values in the back of your textbook for entropy. N and M are the coefficients from the balanced chemical equation. And that's typically how we find delta S. One thing we need to consider is the amount of energy available to do work. That is called Gibbs free energy. And right now, what we really want to get at is using Gibbs free energy, that equation, to determine whether or not a reaction is spontaneous. So a reaction is spontaneous based on both entropy and enthalpy, as well as temperature. When you do that equation, simply delta H minus T delta S, T is temperature in Kelvin. So remember, degrees Celsius plus 273 is Kelvin. The other trick to this equation is that the delta S values are not given in kilojoules. G and H are in kilojoules, S is given in joules. So make sure you convert S into kilojoules beforehand. Otherwise, the equation is quite straightforward. If you calculate delta G and it's less than 0, it's a negative value, it is spontaneous. If delta G equals 0, it means the reaction is at equilibrium. And if delta G is greater than 0, if it's positive, that means it is not spontaneous. In order to make it go, work must be done on it. But the reverse reaction is spontaneous. You know, it wouldn't be AP chemistry without our math. And yes, there is a way to link Gibbs free energy with Q and K. Now remember, Q is the reaction quotient, and it's calculated the same as K. It's just those values are used at any point in the reaction. When you calculate K, you are using equilibrium concentrations. So just a quick review of how you write the expression. There's your equation. Products on top, reactants on the bottom, coefficients become exponents. So often we're going to calculate delta G, and there's many equations we can use. You've already seen the one, delta G equals delta H minus T delta S. If you look at the bottom of the slide, there's another very familiar looking equation. There are delta G values also in the appendix. You can use that as well to find delta G. But when we're talking about standard free energy, we're talking about 1 atmosphere for all gases, pure solids for solids, pure liquids for liquids, solution concentrations of 1 molar. We're at 25 degrees Celsius or 298 K room temperature. And that is what we're talking about for standard free energy conditions. Now, on the next slide, let's take a look at what conditions need to exist for a reaction to be spontaneous. You know that I often stress the need to think mathematically and reason mathematically. Here is a great example. When you use this equation, what conditions make a reaction spontaneous? Well, if you look at this chart, if delta H is negative and delta S is positive, you're starting with a negative number. If you plug in a positive value for delta S, doesn't that make the negative T delta S be a negative value? So what do you have? You have a negative value and another negative value. And when you add two negative values, you always get a negative answer. Therefore, delta H negative, delta S positive, it's always spontaneous. Flip it around. If H is positive and S is negative, well, negative T times a negative value gives you a positive number. When you add two positives, you always get a positive value. Therefore, these conditions always result in a non-spontaneous reaction. But what if they're both negative? So you have a negative value and you're adding a positive, because a negative times a negative is a positive. Well, it could be either one. It really depends upon the temperature. If the temperature is very, very, very small, you will get a negative value. Look at the last row. If they're both positive, negative T delta S will still be negative. Again, you might get a positive value, you might get a negative value. It's only going to be negative at high temperatures. And if you just go and play with some numbers and plug them into that equation, you can prove to yourself that these are the conditions that will result in spontaneity. Let's get back to Q versus K and how that fits in with Gibbs free energy. We haven't talked about this yet this year, although we did last year. K is equilibrium, Q is sometime in the reaction. It might be early, it might be at equilibrium, it might be well past equilibrium. Well, how do you know where you are in a reaction? You calculate Q and you compare it to K. If Q is less than K, there's too many reactants, the reaction will go forward and it will proceed toward equilibrium. When Q is greater than K, it's gone past equilibrium. The reaction will actually go in reverse and to go back to equilibrium. When Q is equal to K, it's at equilibrium. So I always tell this story about you are Q and your friend is K, and you're going to have a picnic at a valley in the mountains. K has gone ahead of you and is waiting for you in the valley. So if you are the first Q on the left, you haven't gotten there yet. Your friend is ahead of you. So what are you going to do to get to K? You need to move forward. If you're the third Q, the one on the right, you went too far. You've got to back up and get back to K. You're going to go in the reverse. But if you find that Q is K, you're in the same location. You are at equilibrium. All right, you've made it to the last slide, so I'll try to be fast. Why do we care about Q and K? Because there are other ways to calculate G. What if you don't have standard conditions? How do you calculate G? You use that equation right there. Delta G, that's the non-standard conditions, equals delta G at standard conditions plus RT natural log of Q. R is the ideal gas constant, in this case 8.314. T is the absolute temperature in Kelvin, and Q is your reaction quotient. But what if you have K? What if you have equilibrium instead? Well, you can use delta G equals negative RT natural log of K. When delta G is negative, you know that K is going to be greater than 1. Think about it. If G is negative, it's spontaneous. The reaction goes forward. Well, if the reaction goes forward, don't you make a lot of products? And remember, K is products over reactants. So if you have a lot of products, big number divided by little number, K is going to be greater than 1. When delta G is positive, K is less than 1. Think about what that means. Delta G is positive. It's not spontaneous. So if it's not spontaneous, the reaction doesn't go. You have a ton of reactants. Small number divided by big number. What do you get? A really small number. Therefore, K is less than 1. When delta G is 0, K is going to be 1. It's at equilibrium. Remember, K is products over reactants. If you do a little bit of mathematical thinking and reasoning like I just did, you don't need to memorize this stuff. It should make sense to you.